You know, deep inside our power grid, there's this unseen backbone doing all the heaviest lifting. Today on The Explainer, we're going to pull back the curtain on the engineering secrets of a component you've probably never even seen, but one that is absolutely essential to keeping our modern world running.
So let's just start with a question that really gets to the heart of it. I mean, we are talking about some serious raw power, a current so strong it's practically a lightning bolt. How on earth do you control that with total, absolute precision? Yeah, 2,000 amps. That's what's flowing continuously through a standard distribution transformer. Think of it like this invisible river of energy that has to be managed perfectly, not just for a day or a week, but for decades on end.
And the answer to that big question? It's the transformer busbar. But, and this is key, it's not just some strip of metal. No way. It's a highly engineered backbone, built to be incredibly robust and reliable, handling all that power safely and super efficiently.
All right, so here's what we're going to cover. We'll look at its role as the power backbone, then the core choice of materials, how it goes from a blueprint to being bent into shape, and finally the finishing touches that make it so reliable.
Okay, first up, the power backbone. Let's really dig into why this thing is so much more than just a piece of metal carrying a current. It's a powerhouse of both structural and electrical engineering.
You see, a bus bar has to be just unbelievably tough. Normally, it's dealing with extreme heat, but during a short circuit, the forces are insane. We're talking about currents that can suddenly spike to like 40,000 amps, creating massive electromagnetic forces that try to tear the part. And it has to withstand all of that for over 30 years.
All right, on to the first big decision an engineer has to make. Which material to use? And this is a classic engineering trade-off, a real battle between two amazing conductors, copper and aluminum. Okay, so this table right here, it really lays out the raw physics behind that choice. You can see right away copper's the clear winner on conductivity. It just carries more current in less space. But then, look at the density. Aluminum is way, way lighter. And that thermal expansion number, that becomes super important a little later on.
So at the end of the day, this isn't just a simple cost decision. Copper is your high-performance, high-strength champion. It's the industry standard for a reason. But an aluminum bus bar that can do the same job is almost 70% lighter. That's a huge deal in a giant transformer. The catch, of course, is that you need a bar that's about 1.5 times bigger to do the same work.
And here's a perfect, real-world case for copper. There was this utility in California. They upgraded their old transformers with tin-plated copper bus bars. And the result? They didn't just fix something, they massively improved performance and basically gave that equipment another 30 years of life. Incredible.
But that doesn't mean aluminum is the wrong choice. It can be super strategic. Check this out. A manufacturer in Texas saved a cool 15% on costs. How? Smart engineering. They used bigger aluminum bars to get the same performance as copper and welded the connections instead of bolting them. It just shows the right design can make the lighter material a real winner. All right, so we've got our material picked. Now comes the really fun part, fabrication. This is where we take a simple flat bar and turn it into a complex 3D shape. And trust me, this is where success is measured in tiny, tiny fractions of a millimeter.
Believe it or not, it all starts with the edges. Now, this seems like a small detail, but it's critically important. A sharp corner creates what's called an electric field concentration, which can literally start to rip the insulation apart over the years, and that leads to catastrophic failure. So a smooth, rounded edge isn't just nice to have, it's essential. This number right here, this just blows my mind. It shows you the insane level of precision we're talking about, 0.08 millimeters. That is thinner than a single human hair. One manufacturer found that just by controlling these tiny little burrs on the metal, they got rid of 80% of their field failures. It just goes to show you, it is all in the details. And here's some cool physics in action for you. When all that current is flowing, the bus bar heats up, and metal expands when it gets hot, right? Well, a 1-meter copper bar will actually grow by 1.7 millimeters. If you don't account for that, the bar would literally destroy its own connections. The solution is so simple, but it's elegant. Just slotted holes. They let the whole connection kind of breathe. Now, bending these huge, thick bars, it's really an art form, but it's guided by some serious science. First, you got to plan the sequence perfectly to keep everything precise. Then you have to account for something called spring back, where the metal wants to spring back a little after you bend it. So you actually overbend it just a tiny bit. And here's the kicker. You punch all the holes first while it's still flat to make sure they're in exactly the right spot. Of course, modern machines make this art incredibly precise. A good hydraulic bender can hit an accuracy of plus or minus half a degree, and you need that level of precision because inside the cramped space of a transformer tank, everything has to line up just perfectly. There's no room for error.
Okay, let's move to the final stage, finishing for reliability. This is where we take that perfectly formed piece of metal and get it ready to survive decades of just relentless work inside that transformer. You know, it's the final touches that really guarantee performance for the long haul, especially at the joints where bus bars connect. By adding a super thin layer of tin plating, you create a surface that's soft and won't corrode. That means you get a perfect electrical connection with super low resistance and one that's not going to degrade over time. And again, we're talking about success being measured in microscopic detail. The perfect tin plating is only 7 to 10 microns thick. That's about 1/10 the width of a human hair. And this isn't just eyeballing it, you know? It's all verified with really high-tech tools like an XRF analyzer to guarantee that exact thickness every single time. Okay, so for any of you engineers watching, listen up because this is a huge takeaway. When you're ordering a custom bus bar, the quality of your request for quote, your RFQ, is everything. You have to be super specific. Give them a 3D model. Call out the exact material grade. Define that edge radius and burr height we talked about. Detail the plating. Everything.
And what this all boils down to is that great communication is just as crucial as great engineering. When you get that checklist right, you don't just avoid expensive mistakes. You can literally cut down your quote times from weeks to just a few days. That gets your whole project moving faster and more reliably.
So think about what we just covered. We went from basic material science all the way down to micron-level precision and the importance of a good checklist. You know, the humble bus bar is just a perfect example of how the biggest, most important jobs often fall to the parts you can't even see. It really makes you wonder, doesn't it? Could it be that the strongest, most critical part of our entire power grid is the one that's completely hidden from sight?